Hello, everybody, and welcome to Science Unveiled. Tonight, we're unraveling one of nature's most captivating spectacles, the rainbow. Have you ever wondered why rainbows form perfect arcs, why their colors dazzle, or why the rainbow you see is uniquely yours? The answers lie in a fascinating interplay of light, water, and your own perspective. Rainbows are more than just bands of color in the sky. They're personal optical illusions crafted for each observer. No two people, not even those standing side by side, see the exact same rainbow. In this special report, we'll explore the science behind this phenomenon, from the physics of a single raindrop to the discoveries that earned scientists a Nobel Prize. Stay with us as we chase the rainbow and uncover its secrets. Let's start with the basics. A rainbow appears when sunlight, raindrop, and an observer you come together. Without your eyes, there's no rainbow. It's that personal. Tonight, we'll take you inside a raindrop to see how light bends and splits, creating a spectrum of colors. We'll also reveal why rainbows vanish through polarized sunglasses and how they've inspired breakthroughs in science. But first, let's set the stage with a question. What makes a rainbow so special? The answer is coming up. Rainbows begin with a simple yet profound interaction: sunlight meeting a raindrop. To understand this, we visited Dr. Emily Carter, an optics expert at the University of Science. In her lab, Dr. Carter demonstrated how a raindrop acts like a tiny prism, bending and reflecting light to create a rainbow's colors. Here's how it works. When a ray of sunlight hits a raindrop, it slows down and bends, a process called refraction. This happens because light travels slower in water than in air. The light then reflects off the inner surface of the drop and bends again as it exits. This journey splits white sunlight into its component colors: red, orange, yellow, green, blue, indigo, and violet, because each color bends at a slightly different angle. Dr. Carter explained, "The key is the refractive index, and a measure of how much light slows down in a medium. For water, it's about 1.33, meaning light travels 33% slower than in a vacuum. Blue light, with its higher frequency, slows down more than red, so it bends more. This bending, governed by a principle called Snell's law, is why rainbows display colors in a specific order, with red on the outside and violet on the inside." To visualize this, we set up an experiment. Using a glass sphere to mimic a raindrop and a laser to represent sunlight, we observed how light behaves. When the laser hits the sphere, it refracts, reflects, and exits at a specific angle, about 42 degrees for red light in water. This angle creates a concentration of light known as a caustic, which makes rainbows so vivid. Each color has its own angle, with violet at around 40 degrees, creating the spectrum we see. But why does light slow down in water? It's because light is an electromagnetic wave interacting with charged particles in the water. These particles oscillate, generating new waves that interfere with the original light, effectively reducing its speed. This phenomenon, studied for centuries, reveals the intricate dance of physics behind every rainbow. Coming up, we'll explore why your rainbow is yours alone and why no one else sees exactly what you do. Stay tuned. Now let's dive into the heart of the rainbow mystery: why no two people see the same rainbow. The answer lies in geometry and perspective. A rainbow forms when billions of raindrops scatter light into your eyes, but only specific drops contribute to the colors you see. Imagine standing in a rainstorm gazing at a rainbow. The red light you see comes from raindrops positioned at a 42-degree angle from the line connecting the sun to the back of your head. Violet light comes from drops at a 40-degree angle. This creates a circular arc centered on your shadow, or more precisely, the anti-solar point directly opposite the sun. Here's the kicker. If someone stands just a few feet away, their anti-solar point is different. They're seeing light from a different set of raindrops, forming their own unique rainbow. Even your left and right eyes perceive slightly different arcs. It's as if the universe paints a custom rainbow for every observer. To illustrate, think of a crowded stadium at night with everyone holding a flashlight. From the field, it looks like a sea of lights, but each spectator sees a unique pattern. Rainbows work the same way. Your perspective shapes the illusion. This personal nature of rainbows makes them not just a scientific marvel, but a deeply individual experience. Next, we'll hear real-life stories of people whose encounters with rainbows left a lasting impact. You won't want to miss this. Rainbows aren't just science, they're moments of wonder that connect us to the world. Tonight, we're sharing two stories that bring this to life. First, meet Sarah Thompson, a middle school teacher from Boulder, Colorado. Last spring, Sarah took her students on a hike in the Rocky Mountains. As a storm cleared, a double rainbow appeared, arching over the peaks. The kids were ecstatic, Sarah told us. They forgot about the rain and started asking questions. Why is the second rainbow fainter? Why are the colors flipped? Sarah explained that a double rainbow forms when light reflects twice inside raindrops, reversing the color order and creating a dimmer arc. That moment sparked a love of science in her students, proving rainbows are powerful teaching tools. Our second story comes from Michael O'Connor, a photographer based in Galway, Ireland. Michael specializes in capturing rainbows over the rugged cliffs of the Atlantic coast. He shared a memorable experience from a sunrise shoot where he photographed a rainbow that seemed to leap from the ocean. When he showed the photo to his assistant, they noticed the colors looked slightly different in person. It was a reminder, Michael said, that every rainbow is a personal snapshot shaped by where you stand. These stories highlight the magic of rainbows, not just their beauty, but their ability to inspire curiosity and connection. Up next, we'll explore the stranger side of rainbows, from double arcs to mysterious fogbows. Rainbows don't stop at the primary arc. In this segment, we'll explore the stranger cousins of the classic rainbow, each revealing new layers of physics. First, let's talk about double rainbows. These fainter arcs appear above the primary rainbow with colors in reverse order: violet on the outside, red on the inside. They form when light reflects twice inside a raindrop, exiting at a wider angle of about 50 degrees. Between the two rainbows lies a dark region called Alexander's dark band, where no light reaches the observer's eyes. It's a striking reminder of the precision of optics. Then there are supernumerary rainbows, faint pastel bands inside the primary arc. These occur in small raindrops where light waves interfere, creating patterns of light and dark. The result, unexpected colors like magenta, a mix of blue and red. Ever tried viewing a rainbow through polarized sunglasses? You might notice it fade or disappear. That's because rainbow light is polarized thanks to reflection at a specific angle known as Brewster's angle. This polarization enhances the rainbow's clarity, but makes it sensitive to filters. Finally, consider the fogbow, a ghostly cousin of the rainbow. Formed by tiny droplets in fog, fogbows appear as faint, often white arcs due to diffraction, the bending of light around small particles. They're a reminder that rainbows adapt to their environment, revealing new forms in different conditions. Coming up, we'll see how rainbows have shaped scientific history from Newton to Nobel Prizes. Rainbows aren't just beautiful, they've driven scientific progress for centuries. In the 17th century, Sir Isaac Newton used prisms to study how light splits into colors, laying the foundation for modern optics. His experiments with refraction and dispersion showed that white light is a blend of all colors, a breakthrough inspired by the rainbow. Fast forward to the 20th century, and rainbows continued to spark discovery. A phenomenon called the glory colorful rings around an observer's shadow in fog caught the attention of scientists studying light's wave nature. By analyzing how light bends around tiny droplets, researchers uncovered insights into wave-particle duality, a cornerstone of quantum physics. This work earned a Nobel Prize, proving that even fleeting rainbows can lead to lasting breakthroughs. Today, the principles behind rainbows inform technologies like fiber optics, lasers, and even medical imaging. The next time you see a rainbow, consider this: you're witnessing a phenomenon that's shaped our understanding of the universe, from the smallest particles to the grandest theories. Stay with us for our final thoughts and a lesson inspired by the rainbow. As we close tonight's broadcast, let's reflect on the rainbow's mystery. Why does no one see the same rainbow? Because each arc is a unique illusion shaped by light, water, and your perspective. Every raindrop, every angle, every observer creates a one-of-a-kind masterpiece. But the rainbow offers more than science. It's a reminder to stay curious. Like Newton and the Nobel laureates who followed, we can find wonder in the everyday and let it lead us to new questions. Whether you're chasing a rainbow in the sky or a dream in your heart, the lesson is clear: embrace curiosity, seek answers, and find joy in discovery. That's all for Science Unveiled. Join us next time as we explore another mystery of the universe. Until then, keep looking up and keep wondering. Good night.